All right. Hello, everyone, and welcome to lecture 10. Congratulations, you've made it to the end of this module. Today, we're going to talk about the last few topics that we will talk about regarding reinforced concrete. Shear design is the element that is missing for us to be able to design concrete structures. We will talk about it today, and we will get a little bit into the design of slabs. So, shear design is a component, a check that you need to include when you're designing reinforced concrete structure. If you miss it, the result is going to be ugly. Shear design has a significant portion of it relies on the strength of the concrete. Concrete, unlike steel, does not give a lot of deformation or warning before failure. Flexure design or flexure failure depends on the yield in steel. And I've explained before how steel yielding gives a lot of deformation, a lot of strain before failure. Shear failure is usually sudden and catastrophic. So you always want to design for flexure and shear to avoid something like that. How can you tell visibly when you look at a beam that is suffering from a lot of shear and it's about to fail? What's that? Yes, the shear crack, the crack due to shear, has a very distinctive characteristic. It is very close to the support and it has an angle. We will talk about this angle today. It has to do with like the angle of the strut of the concrete. The load is trying to work its way to the support. So there is a very interesting model, a very interesting mechanism that we can simplify this process as if this beam has inside it a truss that is trying to triangulate and send the load safely back to the support. So before we get into the angle of the crack and the angle of the truss, let's just like visibly understand what shear is. So if you have a simply supported beam with a point load in the middle, what do you expect the shear diagram to look like? What's that?
A V.
A V? You're talking about something like this?
The bend.
Yeah, that's the bending. Thank you very much. So how does the shear will look like? It's triangle. Yes, rectangle up and down. So you will go like the reaction will go constant. The point load will take it down, and then you will end with 0. So this side, it almost has constant shear. From the point load to the support, this whole part has a constant shear. The beam will start exhibiting some tensile cracks, which are vertical, but then very quickly will result in this 45-degree angle. So, how do you overcome these shear cracks? Last week, we talked about how do we reinforce the flexure cracks. The bending is maximum in the midspan. This is where the bottom vertical cracks are going to have maximum effect. That's why they are in midspan. Most of the forces, there are tensile forces resisted by the bottom reinforcement. The black line is the bottom bars in the beam. The top line is the top black line is the top rebar, and they are useful and significant at the continuous support. Continuous support will have a negative bending at the top, and therefore you need rebar or reinforcement bars at the top and at the bottom. What is the main function of these longitudinal bars? To resist bending. To resist bending. What is the shape of bending failure? It starts with vertical cracks. So if you have a beam that looks like this, it starts with a vertical crack. The crack keeps propagating vertical until the top of the beam is crushed. Do you see how the concrete at the top is turned into rubble, turned into dust? That's the compression block that we talked about. The bottom is the tension in the rebar, and that's the shape of flexure failure. So how does shear failure look like? Shear failure is close to the support, because usually maximum shear is close to the support. It starts with an angle. This angle, this crack, has a range. I would say it's about 45 degrees, and it can go up to 22, 21 degrees. That's the range that the code will reference. So what if the beam is properly reinforced in flexure and properly reinforced in shear? Which is my second question. How do you resist this shear failure in red? How do you resist this crack? I talked about it briefly. I'm curious if you can guess, how do you reinforce the shear crack, the shear failure? Yes, you need reinforcement not in the longitudinal direction, you need it in the perpendicular direction. You need those links, shear links or stirrups. And let me show you very quickly how that works. I will take the far end of the beam where maximum shear is and try to study what is going on. So this is the beam. It is sitting on a support here, and this is the support. What is going to happen is there is a little element from the left hand side. It's feeling the shear going upward. From the right hand side, it has the point load going downward. So it has two equal and opposite forces trying to cause shear. If you look closely, this will turn into a couple that wants to turn or rotate this element. But this element is embedded in the beam. It has nowhere to go. And therefore, there is an equal and opposite couple horizontal. There is an equal and opposite couple horizontal. Look at the vertical component of this shear and the horizontal component. It will result in a resultant of force going this way. The top two, horizontal force to the left, vertical force upward, the resultant is a force going this way. Do you understand where this force came from? It's the resultant of two components of force. A force going down and a force horizontal. This will result in a force at an angle. Always, always in concrete, when you have two forces causing tension, concrete is very weak in tension. It will crack. What is the direction of the crack? Perpendicular to the tensile load. So there is a tension force going this way, tension force going that way. The concrete is very weak in tension, and it will crack in a perpendicular direction to this line. So this becomes the shear crack. That's why the shear crack has an angle going towards the support like this. And it's because of these two forces. And they will keep on causing strain on the concrete till they break the beam into two pieces. So how do you reinforcement? How do you reinforce the tension in concrete? You need steel. That's why it's reinforced concrete. You always need steel in concrete to reinforce the tension. So how a stirrup that looks like this will help close that crack? The stirrup is perpendicular to the crack. This is very interesting. This is very interesting. The stirrup, this is the longitudinal bar. This is the bottom reinforcement, the top reinforcement. And along the beam, I will have a stirrup. In the cross section, this is the concrete cross section. The bottom bars are circles, the top bars are circles, and These vertical black lines, these are stirrups. So I will take an actual bar, small diameter, and bend it into a hoop or a link or a stirrup like that. And I need to wrap it around the reinforcement. You keep putting these links at spacing, at a certain spacing. This is called the spacing of the stirrups. There is a maximum spacing that you shouldn't exceed. If you exceed the maximum spacing, this crack could happen between two stirrups. So what I'm trying to do is, do you know when you get a stapler and you stitch a piece of paper? This is exactly what these links are trying to do. They are trying to hold the top part and the bottom part of the beam so that they don't become two parts. I have interesting diagrams. And this link is resisting that crack by taking this force into two components, the vertical component and the horizontal component. The vertical component of the tensile force will go in the steel, and the horizontal component will go in the bottom reinforcement. So I will talk about this in a second. So before I leave this slide, I want you to understand a few things. Shear cracks are towards the support. They are resisted by links or stirrups, the vertical reinforcement, to hold these two pieces from completely separating. This top part wants to separate from the bottom part, and the vertical stirrups holds them together. So what is the resistance of shear for concrete? What is the shear resistance of concrete? Well, let's first see what shear is trying to do. At the beginning, shear crack will develop if the load on the beam is not very big. You can see just a hairline or very narrow width of crack. Close to failure, this beam will actually turn into two pieces if it's unreinforced in shear. What is a beam unreinforced in shear? Or a beam with no shear reinforcement? Doesn't have stirrups. Thank you very much. If a beam has bottom reinforcement, top reinforcement, and no stirrups, this is called unreinforced in shear. This is a shear failure. If the beam has those stirrups, then you can hold these two pieces together. You can add additional capacity, resistance to resist shear. Very important. So if you miss the stirrups, you'll get a failure that looks like this. If you want your beam to be stronger, you have to add additional reinforcement for shear, which is stirrups. Can you guess where is the most important location in the beam to add stirrups? Is it going to be near the midspan or near the support? Yes, near the supports, because the shear is maximum near the supports. So what are the factors that contribute to the shear capacity? Any guess? What are the factors that contribute to the shear resistance of a concrete beam? Any thoughts? Any thoughts? What are the factors that contribute into the shear capacity of a reinforced concrete beam? Diameter of the stirrup and the strength of steel. Okay, what if the beam has no reinforcement? Does the concrete only the concrete, does it have some shear capacity? Yes, it does. Yes, it does. And this is how we're going to design a beam in shear. We're going to first calculate how much concrete only, with no stirrups, can resist. The second half is if the shear on the beam is bigger than what the concrete only can take, we will help it with stirrups. There are equations for concrete capacity, and there is another equation for stirrup resistance, and this is how you design the beam for shear. So let's take each case at a time. The first case is no shear reinforcement. There are 3 factors that help the section resist shear. There is the direct shear transfer or direct shear capacity at the part above the crack, the intact part of the beam. The beam and the compression block is still intact, so it has some shear capacity. The second part is the crack has an angle, and in order for the 2 sides of the concrete to slide, they have the aggregate of the concrete, the interlock. There's not a smooth surface, it's a very rough surface, and this adds additional shear capacity. And there is a third component called the dowel action of the bottom reinforcement. In order for the top piece and the bottom piece of the crack to completely split, they need to shear off clean the bottom reinforcement. So the bottom reinforcement is also helping a little bit. These are the components that go into figuring out how much is the shear capacity of concrete. So when we look at the equations, it might look overwhelming at first. A whole bunch of symbols and a whole bunch of numbers. We will go through them and realize there's just a few things that dictate the shear capacity of unreinforced concrete. It's the strength of concrete, FCK, and the properties of the concrete and the reinforcement ratio for the longitudinal bars. What if we have some stirrups? Each stirrup is responsible for a volume or an area that is center line to the stirrup multiplied by the width. I also want to add that each stirrup has 2 branches. Do you see how each stirrup has 2 branches? So can I get you to guess what if the area of the stirrup is not enough? I need more steel in the stirrup. What are the options? I'm curious if you can figure out what you need to do if we need more steel area out of the stirrup or the links. This will help take the tensile load to keep to close the crack, or to stitch the bottom and top, the top and bottom pieces together. What if I need more steel in the stirrup?
We can either increase the diameter of the stirrup,
Okay.
thus increasing the area, or we can increase the way the stirrup loops.
The way it loops. What do you mean?
So like, for example, if it's only around that, can't we interlock it in the middle? Create,
These are very good thoughts. Yes. Any other thoughts?
or increase the number of stirrups, like decrease the spacing to 60%.
That's exactly it. I think you got most of the factors. Good job. I'm curious if someone else can summarize if you heard this answer. What are the ways that you can add more reinforcement? Can I get you to guess? How do you increase the steel for the shear reinforcement? If I need more steel, how do I provide more steel for the stirrups? Yes, you can increase the number of stirrups by using smaller spacing. So the first thing is you control the spacing. There is such thing as a maximum spacing. Don't exceed the maximum spacing. We will learn how to calculate it. S maximum should not exceed 75% of D. Do you guys remember what D is? Which distance?
Horizontal?
Horizontal distance.
from the top to the bottom.
Bottom reinforcement, that's exactly it. D is from the very top or from the compression side, from the compression fiber, all the way to the center line of the steel. D. That's the one you were thinking of? Okay. So there is only minimum spacing. Minimum spacing will allow concrete to flow in between the stirrups. Think if you have a lot of stirrups, concrete will have a difficult time flowing in between the stirrups. Do you have a question? If the spacing between the stirrups exceeds the maximum spacing, the shear crack could fall in between two stirrups. The shear crack could develop in between two stirrups and it will have no stirrups to resist it. That's why you shouldn't exceed, so that at least one stirrup goes through the crack. At least one, if this is the crack, at least one stirrup needs to go through it to resist it, to hold the two pieces together. That's a good question actually, by the way. One more thing I will say about this. You can use smaller spacing to add shear reinforcement. You can use bigger diameter, or you can use more branches of the stirrup. So how do you use more branches for the stirrup? I mentioned this one is rectangular. It has two branches. 1, 2. How do you create more branches with the stirrup? Yes?
Changing the shape, so like for example, there was shapes that it's a rectangle, but then the bottom one, it's a V.
Yes.
So that's 5 branches.
Yes, yes. You're mixing, I think the one that has a V, this is the stirrups for a column. But for a beam, especially if the beam is wide. What's that? Yes, yes, that's right. This is the top reinforcement. This is the bottom reinforcement. I could do the following. I could do a link that surrounds the entire section. These are 2 branches, and then I will add on the smaller stirrup in the middle. So now this stirrup has four branches. Do you see how this black stirrup has 4 branches? 1, 2, 3, 4. So use smaller spacing, you increase the reinforcement. Use bigger diameter, or use more branches. All right? Before we get busy with the code equations, I have a video. Let's see if it's gonna work. That shows you. It shows you how the beam will actually fail in shear. The whole idea is you spot the crack when it's not very wide. Otherwise, it will propagate and widen pretty quickly, and that will eventually result in failure. So this is a test in the lab. You can cast a piece of concrete painted in white and trace with a marker the crack when it first starts, and then very quickly you realize the shear crack one is getting wider. And as you increase the load, it keeps getting wider and wider until the concrete pretty much falls apart, and the middle part will just fall and crush everyone underneath it, and the top part will follow pretty much. It's a catastrophic failure. You don't want your structure to end up looking like this. So very important to reinforce for shear design and check for shear design. All right, so I want to feature the concrete Eurocode, which is Eurocode 2, by the way. Eurocode 2 is for concrete design. Do you have a question?
Crack will go 45 degrees.
It ranges between 45 and 22. At least this is the basis of design. We will design the beam within that range. If the angle in your calculation is outside that range, you need to increase the depth of the beam. This beam is too shallow and it's not going to do a good job in resisting shear.
It will fail.
What's that?
45 degrees it will fail.
Above 45 degree, this means the load is very close to the support. I will show you what that means. Less than 45 degree, the crack is going to be very long and it will get mixed in with flexure. It's not going to be a stable structure to resist that crack. So this is the range that we will design for. We will go through the equations, and the range that we will use in the design is between 45, 20, and 22. So there are few things the code will help us and give us some guidelines, and there is no way around it. I need you to open up the design code and read the instructions. Think of it as like the guideline to design concrete structures. It might seem like a lot of information, but in essence, there are a few things that I need you to understand, and I've said it mostly already. There is such thing as minimum reinforcement, minimum shear reinforcement. Do not leave your beam without stirrups. You can use minimum reinforcement. There is another interesting guidance from the code, which is the function of the stirrups is to resist the tension due to shear, and the horizontal and vertical component of shear will work its way into a compression strut. So back to my diagram here. These forces, they have two different components. One component will go into the axial, into the stirrup, and the other component will go into compression with an angle theta. This is the angle that I've been talking about. It's the angle of the compression strut. It's almost the load in the beam is trying to work its way in a truss like this. The black wide strips, this is compression, and it's resisted by concrete. Concrete is very good in compression, so it can resist the wide black members. The thin diagonal members, these are the stirrups. They will resolve in tension. They will resolve the load in tension. It's a pretty good assumption to analyze how shear is going to work its way to the support. Because of this assumption, you will realize something that we can use to our benefit. If the distance between the very top compression fibers to the centroid of steel, D, if this distance is D, then from the face of the support at a distance D, we don't need to include shear within this distance in the design, because any load within this distance is going to directly go to the support. It doesn't affect the tensile capacity or the tension cracking in the concrete. Having said that, if the load is not from the top, it's from the bottom, I need to consider the shear all the way to the face of the support. So this leeway of using the design shear at a distance D from the support only works when the load is from the top. If there is a load hung from the bottom, this still needs support, stirrups all the way to the face of the support. This is the definition of the stirrups and the compression strut. So what is the compression strut? Compression strut is the way concrete resists the shear forces. The shear forces will result into mainly three forces: vertical force, horizontal force, and a diagonal force. The vertical force is tension in the stirrups. The horizontal force is tension in the longitudinal bars. So, shear will add additional tension in the bottom reinforcement. Does that make sense? Does that worry any of you that shear will add more load to the bottom reinforcement?
Shouldn't that be increased?
Yes, definitely. So shear has an effect on the forces in the bottom bars. But the way we do this is we extend the bars beyond the point we need them. If this beam has a bottom reinforcement here, this bottom reinforcement is to resist the capacity this bottom bar here is to resist this moment. Because of the existing shear, I need to extend the bar longer. I need to extend the bar longer to take into effect the increase in tension in the bottom reinforcement due to shear. And you basically offset the moment curve to deal with the tension reinforcement this way. And we can also add the additional tension. We can calculate the additional tension that goes into the bottom reinforcement, so we can make sure that the bottom bars can take the load.
So we're gonna change so how we calculate how many bars we need is by calculating the total area and then divided by total area of steel needed and then divided by the area of the cross-section area of the one steel bar.
Yeah,
To calculate how many steel bars we need.
that's right.
That means the total surface area of steel is gonna increase.
It doesn't necessarily have to, especially if maximum shear does not happen at maximum moment. So what we're gonna do is, we are going to extend the bar and calculate the additional force that goes into these bars and make sure that our section has enough area. Otherwise, you are right. I might need to add more bars based on the shear load. If you have very high shear force, I might need to increase the bottom reinforcement, which is counterintuitive. If there is one thing I need you to understand about this point is high shear forces could result in additional tension in the bottom horizontal rebar. Not just all of the shear can be resisted by the stirrups, because shear model has three forces, has three components. A vertical force in the stirrup, a horizontal force in the bottom reinforcement, and a compression in the concrete, compression strut. And this angle, the compression strut angle, is within the range we talked about.
So in the view, resist
This compression, the concrete. The concrete, yes, the concrete in between this area is gonna form like a strut that will resist this compression force, because the dotted line is compression. The solid line is tension. All right? Very interesting model to understand how shear works its way and how to resist it. You need three things to resist it: tension in the bottom reinforcement. All beams will have top and bottom reinforcement, at least minimum. Stirrups, the code asks us to put always at least minimum shear reinforcement. Unless there is bigger shear, you need more stirrups. And the compression in the concrete, which is concrete is good at. Concrete is good at compression, so it can take that compression. Let's take a look at few equations. Again, this might look more intimidating than it is, but at the very bottom of it is what I explained at the very first slide. Do you have a question?
tension is gonna increase a bit in the bottom and
Yes.
it's gonna result into either extending the length of the steel bar or adding more steel.
Okay, we will always extend the bar. This will always happen. We will always extend the bar, and sometimes we might not be enough and we need to add more reinforcement. So not all the time we will add bottom reinforcement.
Yeah, I get it. But didn't we say that the ratio of steel and concrete has to be equivalent to a certain or to a maximum so that failure in so it doesn't become brittle?
Yes, you're right.
Brittle?
Yes. So make sure you don't exceed the maximum reinforcement ratio.
So we have to do a check at that first?
Yeah. When you design the section for flexure, you make sure that the area steel is within the reasonable amount of steel. If it turns out that you need to add more, make sure that you don't exceed the maximum reinforcement ratio. These are good questions, and it will make sense when we do an example. We'll do it in the tutorial. I just want to walk you through the equations. We'll do the example in the tutorial. I also, before the end of the class, I want to touch on the design of slabs. So what this is basically is explaining the design of shear with no stirrups, because concrete on its own can resist some shear. So how do we figure out the shear capacity for concrete only? It's this equation over there. So most of these symbols, you will realize it depends on pretty much two things. The geometry of the cross section, the width and depth. Row 1, which is the reinforcement ratio of the longitudinal bars, because the longitudinal bars help with the dowel action. And the compressive strength of concrete, FCK, which will give us an indication of shear or aggregate interlock and direct shear transfer at the compression block. So when you walk through these symbols, you will figure out that they depend on the concrete strength and the longitudinal bars in the bottom. There is one more element that could enhance or reduce the concrete shear strength. I'm curious if you can think of it. There is one more element that can increase the shear capacity for concrete or could decrease it. Could be actually a negative and be a source of a headache.
Water.
What's that? Water? Water, especially if it has salts, it could get into the cracks and cause corrosion, and this will damage everything. This will damage steel, and this will result in lower shear and moment capacity. Yes?
The surface of the aggregate.
The surface of the aggregate.
So like if it's from
This is a factor. Yes, this is a factor, but I would say it's within the code tries to give us reasonable assumptions, so we don't rely too much on different areas of aggregates. It is a factor. Do you have another thought?
Type of connection near the type of the connection.
Connection between what?
The column and the end of the beam.
It's especially if the beam is sitting in bearing, the shear capacity of the beam is not going to rely much on the connection. What will affect the shear capacity of concrete is axial load. You know, bending, shear, and normal force distribution. What will happen if you have a shear crack like this and there is a compression, axial compression on the beam? It's going to make it harder. It's going to make it harder for the shear crack to slide. You know how friction works? Is like normal force and the coefficient of friction. Coefficient of friction is taken into account with the aggregate interlock. If there is compression force, it makes it more difficult for shear to slide. Can you guess what will happen if this beam has a tension on it? it's easier to break. It will reduce the shear capacity. So the code will ask you what is the normal force or the normal stress on the beam. If it's compression, it will add to the resistance. If it's tension, you subtract it. So you put the correct negative or sign for the force. I need to emphasize this. Would you consider any compression on the beam to enhance the shear capacity?
No.
Any compression would enhance the shear capacity? Would you consider any compression to enhance? Permanent, right. You don't want to consider compression that is just going to happen for a little bit and then will be released. So I would consider compression only from the dead load. The permanent dead load that has no chance of not being there. Otherwise, it will be more conservative to neglect the compression. Always include the tension, because the tension makes it worse. So it could fail when tension arrives. This is how you calculate the shear reinforcement, and the resistance will depend on few things. The area of steel. What is the area of this stirrup? Take a cross section in the stirrup, count the branches, multiplied by the area of one branch. All right? So the ASW is the area steel for shear. How much is ASW? Yes. I just explained it. Yes? You take, and then what happens? Multiply the number of branches multiplied by the area of one branch. All right? S is the spacing. Yes, go ahead.
In this case, which area do I take? I take the area of, so I take the vertical area or the rectangular area?
No, the area of the stirrup bar. The area of the stirrup.
No, I know, I understand the area of the stereo, but then, because there was an example where we used two different areas of the steel. So one is the diameter of the circular area of steel, and then the other one is because we're looking at it from the side, we're not looking at the circle.
Yeah.
So we're taking the rectangle.
No, you take the area of the cross section, the circle. All right? So these are the factors. Smaller spacing will result in bigger stirrup resistance. Big spacing, it's inversely proportional. All right. I think an example with some numbers will make all these equations easier. But before I let you go, I need to start a discussion so the example in the tutorial makes sense. I want to talk about the design of one-way slabs. The design of one-way slabs. Let's say you have a floor system that looks like this. This is an elevator shaft. These are elevators. These are voids. This is a staircase. And this is how you enter this building. This is a floor of a multi-story building. This is a plan. We're looking on top of the building. So you could have like apartments here, you can have desks, this could be a hospital, but the structural layout is columns. All the rectangles are columns. The dotted lines are beams. So can I get you to guess what is the shape of the cross section? When you take a cross section parallel to grid line 4, can I get someone to guess what a cross section to grid line 4 would look like? Yes, that's right. So it will look like this. You will get a beam, and then a little bit of a slab, and then you get another beam, and then a little bit of a slab, then you get another beam, and you continue to the end of the floor. This is grid line A. This is grid line B. This is grid line C. Do you see what I'm doing? I just took a cross section here and look sideways. So this is grid line A, B, and C. What is happening inside the concrete? What do we need to place inside the concrete? Steel, reinforcement, right. So we'll have to show reinforcement as well. Each beam will have a stirrup, top and bottom bars. Each beam will have a stirrup, top and bottom bars. All right? How do you reinforce the slabs? You can think of it as like a beam, but very shallow. All right? It depends on the spacing or the span. This is the span. We can estimate a thickness of the slab. This is T slab, or the thickness of the slab. You start with an assumption, a guideline, depending on the system. Is it one-way slab, or is it a beam, or is it a two-way slab? It's a ratio of the span. So it could be like, for a simple beam, you start with a depth relative to the span divided by 10. This is a simple beam. You can divide by a bigger number for one-way slabs. All right? So let's say like the thickness is going to be reasonable with 150. You might get away with one layer of reinforcement. You might get away with just the bottom bars. So there's a bottom reinforcement here and bottom reinforcement there. If the thickness is bigger, when you get to 200 millimeter slab, 250, you need two layers. You need bottom reinforcement and top reinforcement. Even for the one layer, at the supports, I need top reinforcement. Do you guys can guess why I need in the midspan bars in the bottom and at the support bars at the top? Tension and compression. What do you mean then?
The support بتشيل tension at the top when you push continuously.
Okay, what is the relationship? Yes, you're right. What is the relationship between tension, compression, and the reinforcement?
The tension
So where do you want to put the bar? Exactly. All right. So can you guess what is the bending moment diagram for this beam if there is a distributed load acting on it?
negative at the support and bottom at the midspan and maximum.
So where are the supports? What is supporting the slab? The beam. So at this grid line, there is a support. At this grid line, there is a support because the beam is supporting the slab, and there is another support here. Due to this load, the bending moment diagram looks something like that. Do you guys agree? Negative at the support, positive at midspan. And this is exactly how you reinforce the slab. You put steel on the tension side. Steel tension side is in the bottom, you put the bar in the bottom. Tension side is up, you put the bar at up. How far do you extend the bar? Well, you need to go past the bending moment and then extend it a little bit because of shear. We talked about how the shear will add additional extension to the bar. So these are all detailing issues, but in terms of calculating the reinforcement, can someone guess how do you calculate the number of bars at the top and bottom? Total area ratio, like you want to put minimum reinforcement? What is the main factor that will dictate the number of bars?
The area, the load of this area.
Right. So what are the straining actions? Is it the shear or is it bending that will mainly dictate the area of the bars? Bending is for horizontal top and bottom. Shear is for stirrups. So because the slab is very shallow, there's usually not enough space to put stirrups. So we will rely on the compression, on the shear capacity of concrete only. And because it's very wide, so it will have usually, most of the case, sufficient capacity. Before I leave this, I want to point out a few things. First is, how do you design a section for flexion? Last week we designed a beam for flexion. How do you design a slab for flexion? This is a slab. We designed the beam last week. How do you design a slab for bending? So how do you design a beam for bending?
First, calculating the compression force and the tension force, and then you
Yes.
calculate how much.
Yes, exactly. You calculate the compression block, the neutral axe, the...
You do the same thing for slab?
Yes. This is the tension, this is the compression, and this is Z, and you apply in the equations. What would the cross section of a slab look like?
Only. Only sorry, main bars.
All right, so what is the width of the slab?
It's gonna be.
This is B, this is the width of the beam, and this is the height of the beam. What is the width of the slab? This is very important question. When you design a slab, the slab is like pretty big. What is the width of the slab?
لا بيبقى أقل شوية صح؟
It's spanning between two beams. Oh, you mean the span of this beam? That's the yes, you're right. That's the overall width of the slab. But we don't need to do that.
We can take a small cross section.
Yes, okay, this is,
Same.
how much would you take?
Like 2 meters by 2 meters.
I would take 1 meter strip. Just 1 meter wide of the slab. And every meter, I'm going to put the same number of bars. That's why you calculate the bars per meter. You will put 5 bars, that much diameter per meter. And then you calculate the spacing between the bars this way. So I like this very much. So the cross section of the beam will be a 1 meter strip. All right, and this will be B. You can take it as 1,000 millimeters. How much is the height? The thickness, right? So if that was like 150, 200, whatever the thickness is. So where are the bars? Top at the support, bottom at midspan. Yes. So there you go. 1, 2, 3. And then you can calculate the number of bars you need per meter. And then from there, you can calculate the span, the spacing between the bars. I have one more thought about this and then I will let you go. Do you guys want to include this in the discussion? No? Okay. I find it very distracting. So you've been continuing this for a while. Do you want to join us or do you want to continue the discussion elsewhere? So you're gonna leave it there? All right. What is this? Why it's not smooth like this section? Why it's broken like this? I talked about this. I mentioned this before.
The extension because of the shear. The extension because of the shear.
Okay. No. That's an interesting thought, but it's a different diagram. The extension because of shear is a different diagram. Why the bending moment? Why these two lines are not in the same point? Why they're shifted? Yes, because of case of loading. This diagram takes into account what if the load is maximum in midspan and no loads in opposite directions, or maximum negative with the two adjacent spans loaded. All right, so how many sections I need to design? I need to design a section at midspan to figure out the bottom reinforcement, and I need to design a section at the support to figure out the top reinforcement. When you try to plot this, it looks something like this. This is the bottom reinforcement, this is the top reinforcement, and there are dots. There are dots here. So the main reinforcement is bottom. What are these opposite direction bars doing? So this is grid line A, this is grid line B. This horizontal bottom bar is this line. There is another line perpendicular to it. There is another bar perpendicular to it. What is this bar? This is a very important concept. Even though the main stresses are in the short direction, I need to provide reinforcement in the other direction as well to control shrinkage, cracking, and usually it's minimum reinforcement. So I will put main reinforcement in one direction as a layer, and then perpendicular to it, there is another layer. All right? So the short direction, you will calculate it from the bending moment. The perpendicular direction, you could provide minimum reinforcement. Just follow the code equation for minimum reinforcement for slabs to control shrinkage. Otherwise, the beam or the slab could be safe, but the serviceability is not going to be controlled at all. You can walk underneath it and you see cracks in the direction that is not reinforced. All right? So that's pretty much it, what I wanted to say. Let's take a break and then we'll take some examples to cover these parts. If you have any questions, come see me. If not, I will see you in the tutorial. See ya.
طب هو الحاجة يا دكتور نركز على